is Michael Sander, and I'm going to present you our work on momentum residual neural networks. This is a joint work with Pierre Ablin, Mathieu Blondel, and Gabriel Perry. I will start with some background on residual neural networks. Residual neural networks, or ResNets, are a key element in many performing state-of-the-art deep learning models. Due to the depth, their residual structure makes them possible to achieve. Consider a scalar loss L of x and theta to minimize. The backpropagation algorithm requires to store all the values of the extents, the activations, at layer n. This becomes an issue in increasingly deep architectures because the memory requirement to store the extents is simply too big. One solution, however, is to recompute iteratively the extents during the backpropagation iterations. This gave birth to invertible models, among which neural ODEs, iResNets, iWaveNets, and RevNets. However, they all rely on constrained architecture so far, where it's necessary to change the neural network F in order to make a model invertible. What we propose in our work is to simply change the forward rule of a ResNet by adding a momentum term. Consider this forward rule, xn plus 1 equals xn plus f of xn. One can simply modify it by adding a velocity term v and a momentum term gamma as follows on the right-hand equation. Note that setting gamma equals 0 on the right equation re-gives the ResNet's forward iteration. This construction is a dropping replacement for any ResNet because a ResNet can be turned into its momentum counterpart only by changing the forward equations. Both models take the same parameters as input. This formulation is also exactly invertible, meaning that one can recover the value of xn and vn knowing the values of xn plus 1 and va plus 1. This also avoids the memory bottleneck, as shown in this figure. Theoretical properties of momentum ResNets can be investigated in the infinitesimal step size regime, where ResNets can be seen as first-order ODEs. As such, they can only model homeomorphic dynamics, meaning that, for instance, they fail to separate two nested rings, as shown in this animation. In contrast, in this framework, momentum ResNets are seen as second-order ODEs, and as such, they can model non-homomorphic dynamics and crossing trajectories. In our paper, we showed that momentum ResNets have better representation than ResNets. See how they achieve to separate two nested rings. I will now present some experimental results. First, the important memory gains are confirmed in practice. In this figure, we see how a momentum ResNet can consume half the memory a ResNet would and achieve a similar accuracy on an image dataset. Another important feature of momentum ResNets is their ability to perform pre-training and fine-tuning. For instance, in this experiment, we took a ResNet that was pre-trained on the challenging ImageNet dataset. We transferred its weights into a momentum ResNet using the drop-in replacement of momentum ResNets. In only 5 additional epochs of training, the momentum ResNet achieved a state-of-the-art accuracy on the ImageNet dataset. What we then did is we compared the ability of both models on the fine-tuning application on a whole new dataset. We took benefit of the memory gains of momentum ResNets to process batches that were twice larger than for ResNets, and this was sufficient to obtain a training time that was shorter in order to obtain a good accuracy on the new dataset. Many other experiments are available in the paper, showing the impact of the momentum term gamma, showing the impact of having second-order ODE blocks in the neural ODE framework, showing also the learning curves of momentum ResNets on the ImageNet dataset, and how momentum ResNets can learn to optimize where RevNets, another popular invertible model, fail. We also release an open-source Python package that can be installed through the command pip and is available at this website. It has a method called transform that takes as input a ResNet that is, for instance, pre-trained on the ImageNet dataset and returns its momentum counterpart, only specifying the value of the momentum gamma. It's really a plug-and-play package that we encourage to use. Thank you very much for your attention.